Okay, so starting from today, we're going to discuss the fifth unit, which is functions. We just skipped unit 3 and 4 because those were covered in the other course, so I don't think we need to do it again. We got the now chapter for this unit. Functions, we have a lot of topics to talk about. And then we have another noun chapter or unit 6 for probability. So we still got a lot of things to cover. So let's just start from the first section for this unit, defining functions. Okay, we all know the functions from the very starting course of algebra, but we just define everything in a little different way, in a more formal way in mathematics, in abstract way. Everything you have learned is true, but we have to use a little different language. We have to use, for example, the language of quantifiers. We just covered the logic in the last unit, so we can use those symbolic logic in the definitions and in functions in this topic. So the first question is, what is a function? We already learned, x and y, a pair of numbers. We call it coordinates, and the function is a relation that only one number is paired with the x coordinate, only one y coordinate, to pair with the any x coordinate. So it's a special type of relation. Since we already defined relations based on the sets, so we're going to use the same strategy here. Okay. So the first thing to recall that we define the relation from set A to set B to be a subset of A cross B. Remember, what is the definition of the product of two sets? This is general, by the way. This is a general definition that can be applied in many topics in mathematics. The product of two sets that can be, for example, used to define product of the groups, Cartesian products of groups. But when we say the product of one set to another, we mean the ordered pairs, right? That's it. All the ordered pairs in the form of A, B, where A is from set A and B is from set B. A is the product of the two sets, Cartesian product, the two sets, remember. And the relation is just a subset that you just pick up any ordered pairs from this A cross B. Whatever you pick up, it makes a relation. So relation is very broad definition that they can include any kinds of ordered pairs. So that's the relation. So of course, function is a special type of relation that we have to satisfy certain conditions in this definition one. Okay, that means for any element in the first set, we only have at the most, actually, you know, um, uh, one element B corresponding to it, and we should have exactly one element in A that has one element in B, paired with it. We need to include all the elements in A in the definition of the function. So that makes the function a set of all the pairs. All right. So so the important thing is that when you define a function, that then all the elements in set A must be included in this set of all the pairs. Okay. So let AB be sets. The function from A to B is a relation F from A to B. That is a subset of A cross B, as we know that, such that each element A in set A is the first coordinate of exactly one element of F. All right. So this tells two things. First, that each element in set A, so when you define the function, then it has to include all the elements in the first set. All right. And second, it says its first coordinate of exact one element. So it cannot appear twice as the first element in this set. All right, or in this relation. So in other words, if you write this definition in symbolic logic, we can say for any element A in the set A, there exists uniquely. Okay, this you already saw that existential quantifier, and if you put this next to it, it means uniquely. Okay, that means uniquely. So there exists a unique element B in the set B, such that this ordered pair makes the function f. Okay, so it includes all the pairs of all the elements from the first set and paired with element in set B. And you cannot have a pair with the same first coordinate but different second coordinate, as we already know that. But so that's the symbol logic to define the function. Okay, so that includes all of those order pairs. And we have a name for the set A and the name for set B. We call set A the domain of F, and we call B the codomain of F. Okay, remember, we don't say it range. It means a different thing. Range is not the same as the codomain. This set B is called the codomain. Okay. And the range actually includes all the elements B in this order pair of the function. So that means some of the elements in set B may not be included in the function f, although all the elements in set A must be included in the function f. All right, see the difference? So we call this codomain. So codomain is contained in the range. All right, it's larger than the or equal to the range. Okay. Well, sometimes we write, in another notation, like let f a F colon A, set A, arrow B be a function. So that means the same thing as the definition in here. Okay, so that gives us a little different way to define, the function, but it's more precise. Okay, all the concepts are precisely defined. So, for example, if we have two sets A and B with four numbers, A, 1, 2, 3, 4, and 5 numbers in B, 1, 2, 3, 4, 5. And then we can define a function f as the set of all the pairs of 1, 2, 2, 2, 3, 4, 4, 1. Okay, so that f is a function because each of the four elements of A, 1, 2, 3, 4, is the first coordinate of exactly one order pair in F. So any numbers in the set A does not appear multiple times in the other pairs. Okay. But you can see, if you look at the second coordinate of the other pairs, it only includes 2, 4, and 1. 2, 4, and 1. So the number 3 and number 5 are not included in the function f. All right. So that's why it's called codomain. B is called codomain. And you can see, f can be represented in different ways. In here, we just write in all the pairs, but you can also represent the function by a formula in many cases, and even in graph. All right. But originally it's defined as the set of all the pairs. That's the original definition of the function. Okay, let's see how do we draw the graph of the function or diagram. Okay, so if we just draw two sets A and B side by side with all the elements or numbers explicitly shown up. Okay, so we got 4 numbers instead of A and 5 numbers instead of B, right? And then we just indicate the correspondence between the two sets element by element. So in this example, we have 1 goes 2, 2 goes 2, 3 goes 4, 4 goes 1. So we got both 1 and 2 in set A correspond to 2 in B. All right, so both 1 and 2 in A go to 2 in B, and 3 goes to 4 and 4 goes to 1. Okay, so let's just draw those correspondence by arrows. All right. All right. So if you look at the graph, then when f is a function, we have exactly one arrow emanating from each element of the domain. All right. So that's why you cannot have two pairs with the same first coordinate, but the different second coordinate. Okay, so there's only one arrow going from each element inside A. And there's no such restriction on the codomain. So you can see, both 1, 2 inside A go to the number 2 instead of B. So So in the codomain, the number 2 can correspond to two different numbers instead of A, and that'd be fine in the function, as we already know. Some elements of the codomain may have multiple arrows pointing at them, and others may have no arrows pointing at them. So you can see the number 2 instead of B has two numbers going from A, but the numbers 3 and 5 do not have correspondences inside A, and that's perfectly fine for a function. Okay. So pretty straight. Okay, so let's see another example. We have two sets A and B, and the set A includes 5 letters A, B, C, D, E, and the set B has three numbers 1, 2, 3. So we can define any relation between these two sets by the ordered pairs. For example, if we define relation F as the ordered pairs, the set of ordered pairs of A1, B1, C3, D3, A2, and that's perfectly fine because as long as the first coordinate is from the first set and the second coordinate is from the second set for any other pair, then it will be a relation, all right? And this relation is not a function as you see, first, it's easy to see that the element A in the set A has two correspondences in set B. It goes to 1 and it goes to 2 also. As you can see, the diagram also shows clearly the two arrows going out from A inside A. But that's just the one reason, and there's another reason, why this is not a function, and people may easily skip it, and that's because the element E inside A, remember, that's also element E. It does not have a correspondence in the second set, We don't see E in the first coordinate of the other pairs in the F. And you can clearly see in the diagram also that the element E does not have any arrow going out toward the set B, and that's that's not a lot. When you attack a function, then each element in the set A, in the first A, must have a correspondence in set B. All right. All right, so that's another example, and hopefully this should clarify some concepts about function. Okay. All right. Let's just have some more definitions and to refresh your memory. Okay, so the other thing about the notation, okay, for relations, if you still remember how we write relations, we usually write A or B. So for any other pairs in a relation, we just write the first coordinate, first element, which is from the first set, and then R, the relation, representing the relation, and the B, which is from the second set. For any other pair in the relation, we just write this. To mean it is a relation, okay. from A to B. And this order pair of AB is in this relation, okay? So that's one notation for the relation. But in the functions, we don't use that too much, as we know. We usually write f of A equal to B. If you define a function f from A to B, set A to set B, we usually write f of A, small a equal to small b to mean this ordered pair of AB is in F. But it actually means, this relation. Okay. So this notation essentially means ordered pair. Okay. Always keep in mind that the relation function is a set of ordered pairs. Okay, it's a set of ordered pairs. All right. So from this notation, f of A equal to B, A is the first coordinate and B is the second coordinate of the ordered pair. All right. So this is this basically gives us a one ordered pair in the function. Okay. And we have a spatial term for this B. Okay, if f of A equal to B, we say that B is the image of A under the function f. Okay, so B is the image. So that's another term. Keep in mind. And you might have learned this before, but just make sure you know these things. Well, let's just look at another example. The two sets A and B both include 4 numbers. Set A includes numbers 1, 2, 3, 4, and set B include numbers 5, 6, 7, 8. So we can define the function from A to B, set A to set B, as the set of all the pairs of 1, 5, 2, 6, 3, 7, 4, 8. So we usually write f of 1 equal to 5 instead of the pair of 1, 5, and f of 2 equal to 6, and so on. That's what you have learned before. But you can also write in other pairs, okay? So the image of 4 on the F is 8, right? So 8 is the image of 4 on the F. And, we can just say the image of 4 is 8. The image of 4 is 8, and we know we're talking about this function, so we don't have to specify we're talking about the function f. Okay. So this is another example in here. A function f from A to B, set A to set B. One example before. 24.5. I think we just yeah. So this is the same example. You can see if you look at the pattern of this function defined, the function f, you can see the y coordinate is just the x coordinate plus 4. So 1 plus 4 equals 5 for the first pair, 2 plus 4 equals to 6 for the second pair, 3 plus 4 equals to 7 for the third pair, and 4 plus 4 equals to 8 for the fourth pair. So then we can write this function in another form in addition to all the pairs, the set notation, and this notation specifically of f, and each element, so each number writing down in this way. We have another way to write the function. We can use a formula, for example. we can write for each element A in the set A, we have f of A equal to A plus 4. So, so I just said, you just add 4 to the first coordinate to get the second coordinate. So, so for example, the pair 1, 5 belongs to F, and the pair of 2, 6 belongs to F, and so on. So, so that's another way to write the function, but you can also write in a short notation like this. So we can write F equals the set. Remember, a function is a set of all the pairs. So that is all the pair of A and A plus 4, where A is from set A. Okay, so that's another way to write the function. And this is, you might not see this too often, but you can write in this notation. It's a set in any case. Okay. So obviously you can draw the graph function. This function f, for example, the parabola. So this function is defined as the ordered pairs of x, x squared, where x is a real number, so it includes all the real numbers. So it gives you a parabola opening up. Okay. So this function is from R to R. Okay. So R is the domain, and also is the codomain. But one thing okay. Okay, that's fine. I understand. Okay, so you see the codomain R includes all the real numbers, but the range does not. Okay, so they're not the same. But the domain includes all the real numbers. So this curve goes from the far left to the far right without the end. Okay, so that's called the graph of the function. All right. Actually, we don't also write this kind of notation too often, in the set notation. We just write a formula in most cases. But remember, originally the function f is defined as the set of all the pairs. Okay. Well, the other thing to be cautious is that when you define a function f from set A to set B by a formula, and then you must make sure that the image of each element in set A is in set B. Okay, if you have an image of element in set A out of set B, then it's not a function. Okay, it's not a function. Okay, so so for example, if we define a function f from R to Z, so R is the domain and Z is codomain by the formula fx equals x squared for all real numbers x. Okay, does that give function? It is not. Okay, and the reason is that the domain of the function is all real numbers, so you can plug in any real numbers, but the codomain is just the integers. So if you plug in a fractional decimal, you may get another fractional decimal, which is not an integer. Okay, so so this function, I mean, this is not a function from R to Z, although you do have this formula, and you have the domain. It does not define a function from R to Z. So that means you need to change the codomain Z to R to define a function. Okay. So just be careful about these small things to make it precise. We didn't, I don't think, you discussed so many details about it, So we have to make everything to be precise. Then the next definition is about equal functions. If you have two functions, f and g, what it means by they are equal. If they have the same domain, the same codomain, they are equal as sets or the pairs. So everything has to be the same. This is especially important because, if you don't have the same codomain, then they're not equal. For example, although you may have the same formula and same domain, they may not give you the same function if you just change the codomain a little bit. So for example, if we define a function f from z to z by fx2x, okay. So that's indeed a function because, when you plug in an integer for x, you multiply to get another integer, right? And it is, you only have one number corresponding to each x for f, okay? So that's function. Similarly, if you define another function g from z to r by the same formula, 2x, that's also a function, all right? For similar reasons, but they are not the same. Although they have all the other pairs, all of the other pairs are integers. Okay, so they are exactly the same, but they're not the same function because the codomains are not the same. The codomain of the first function is z, and the codomain of the second function is r. They're not the same, so they're not the same function. So you can see codomains can be different, and codomain is not the same as the range. That's once again you can see that. So so we just do these things very detailed and very carefully. Another example is if we define f as 2x plus 2 again from z to z, and we define g also from z to z as 2 times parentheses x plus 1 parentheses back, and then these are two equal functions. First, there are functions, okay, and they are exactly the same. They are equal because they have the same domain, so same codomain, and the same order pairs. If you distribute 2 into x plus 1 in g, then you get 2x plus the exact same thing. So you get same order pairs. So everything is the same. So these two functions are equal. Okay. The next thing is called piecewise defined function. This is something that really makes a lot of confusion for students. So how do we define piecewise defined functions in mathematical language in pure math? We have to use sets, basically as a basic foundation to define, these terms. So let A and B be sets. So again, we have one set A and one set B. And suppose that the set of PQ is a partition of A with 2 parts. So you just divide the set A into 2 parts, P and Q. They are disjoint, okay? by partition, it means they are disjoint. You don't have anything in common between the set P and Q. Okay, P and Q are two sets also. Okay, and the union of P and Q is A. So that's how that's what it means by partition. You cut the set in different parts, and there's no overlap between any two parts. And similarly, we can we can do the set B, but let's just talk about set A first. You can actually partition B also in the definition of piecewise defined function. So let's just say we are given a function g from P to B. So P is part of A, okay, subset of A from set B. So that's a function, and H is another function from Q to B. So that's the other part of A, set A from B. Okay, so they have the same codomain B. All right, but different domains P and Q for these two functions. Then you can take the union of this G and H, define a new function from as a f. We call this a f from A to B. Okay, so that's called the piecewise defined function. So always keep in mind, when we talk about function, it is a special type of relation, which is a set of ordered pairs. So then each function G and H is a set. It's a set of all the pairs. So then you can take the union of the sets to get another set, and actually you will get a function we call it f from A to B. All right. Okay, so we usually write in this notation for piecewise function. We write f of A, which is the element in A, equals G of A if A is in P. Okay, so so we're talking about the function G, right, from P to B. So when A is in P, then this function value f is actually the same as function value as G, right? Okay. If A is in Q, in the other part of the partition, then the function value is the same as H of A. All right. So that's typically the notation for piecewise defined functions, and we already see that quite a bit. All right. So I guess we don't have time to prove it today, so we're gonna do the proof next time. But this is a theorem actually. It just tells the union of these two functions gives another function. So we need to prove the fact, and it's not hard to prove, but we don't have time for that. So we're gonna do it next time. Any questions?